This video is just a brief introduction to gases. It will be the notes packet, just the first couple pages. This is stuff that you guys have had. I know that if you had me last year, if you had Mrs. Sorensen at some point in time, you did a lot with gas laws. I know you did the egg in the bottle and the marshmallow in the syringe and shrink wrap person. So you've done a lot with pressure and gases. So you have some idea of these conceptually, at least. Maybe not mathematically, but you have an idea conceptually. So first thing here, I think you know all this stuff. How does temperature, pressure, and moles of gas affect volume, I guess, first of all? So how are all those related? Well, you know some things here. We've got a syringe. Pressure and volume you kind of know. If we put more pressure on this gas, which is confined, more pressure on it, the volume goes down. So an increase in pressure causes a decrease in volume, and vice versa. If there's less pressure, the gas is free to expand, spread out. So you always think about the molecular motion. Temperature, obviously, as you heat a gas, the molecules increase in kinetic energy, causes more collisions with more force, molecules spread farther apart. So an increase in temperature causes an increase in volume. And moles of gas. If I blow more moles into a balloon, the balloon takes up more space. So more molecules cause more volume. This syringe, if these are at the same pressure and temperature, this one's got more moles of gas in it than this one. It's the only way that it can be bigger. So an increase in moles, which is N for a symbol, N is moles, causes an increase in volume. So we have a direct proportion, one goes up, the other goes up, or vice versa. Direct proportion, inverse proportion. So if we write those as ratios, you guys are used to direct proportions. I would write this as V over T equals V over T. In other words, that ratio will stay constant as long as pressure and moles of gas is the same. This one I can write as V over N equals V over N, or flipped around. This ratio, I would say that P times V equals P times V. So as this gets bigger, this gets smaller. That ratio can stay the same then. Okay, one goes up, the other goes down, so these will always be equal. These, if one goes up, this has to go up with it in order for this ratio to be the same. Okay, so for all of these, this only holds true. Pressure increases and volume goes down only if we're holding temperature and moles constant. Okay, so for example, if we have this gas in here, if I would double the temperature and double the pressure, the volume would not change. You think about that. If I double the pressure, the volume gets cut in half. Doubling the temperature, the volume goes back to where it was. Okay, so they all kind of work together. Actually, these ratios are these down here. Now I can combine all those together. Okay, you may have seen last year, Ms. Sorensen might have done PV over T equals PV over T, possibly at some point in time. But we can combine moles in there. We can say that this ratio, for every gas, that ratio stays consistent. For every gas, that ratio stays consistent. You take the pressure times the volume, divided by the moles, divided by the temperature. Doesn't matter if I have this much gas or if I have this much gas. This ratio will always stay the same. It's always the same answer if I plug those things in. We'll come back to that at some point in time. So since this ratio stays the same, we can set that up as this. PV over NT equals PV over NT. So these are called final and initial state problems we'll use this for, where I have a gas at these conditions. If I change any of these four things, what would change with it? Next part of this, molar volume. Okay, a mole of any gas. Doesn't matter if it's hydrogen gas, this is important. Hydrogen gas, water vapor gas, methane gas, carbon dioxide, doesn't matter, a mole of any gas at STP, at 0 degrees Celsius and 1 atmosphere pressure, a mole of any gas takes up 22.4 liters of space, this box. Okay, so if you're at STP, 1 mole of gas would fit in this box. So we're not at STP right now. We're pretty close. So there's 1 mole of air in here. Now, 20-some% of that's nitrogen. 70-some% of that's nitrogen. 20-some% of that's oxygen. But there's a mole of gas molecules in this box if we are at 1 atmosphere and 0 degrees Celsius. Okay, now we're not in this room. We're a little bit hotter than that, a little bit less pressure. So that means there's actually less than a mole of gas in here because the molecules are a little bit more spread out. So in this room, we cannot use that. We cannot say that 1 mole of gas is 22.4 liters, only at STP, 0 degrees Celsius, 1 atmosphere. Remember, 1 atmosphere is sea level. Next part of the sheet, I just got some pressures. I am not going to do those conversions. You guys can do those on your own. Okay, but there's a bunch of different pressure conversions. You know, kilopascals, 101.3 kilopascals is equal to 1 atmosphere of pressure. 760 millimeters of mercury, which is just how high the mercury is in the barometer, I'll show you what I mean by that, is equal to 1 atmosphere of pressure. Okay, so all of these things are equal. 760 torr is the same thing as that. Okay, so that part you guys can do those conversions. Next part of this, Avogadro's law. Equal volumes of different gases. So if I have 5 liters of hydrogen and 5 liters of nitrogen, if they're the same temperature and pressure, it's the same number of moles. It's the same number of molecules. Okay. The reason is there's space around gas molecules. So it doesn't matter how big the gas molecule is itself. It makes no difference in how big the molecule is itself because there's already some space around it. Okay. I'll talk about that a little bit more so you guys understand that a little bit better in class. But, so which contains more moles of gas? 10 liters of hydrogen, 10 liters of carbon dioxide. They'd be the same. If we were at STP, they'd be less than a mole because it takes 22.4 liters for a mole. But 10 liters could be a mole if we're at cold temperatures, high pressures. Which has more molecules, 10 liters of methane or a mole of NH3? Well, if we're at STP, this would be way less than a mole because it takes 22.4 liters to be a mole. So this would be a lot more molecules if we're at STP. If we're not at STP, then those things could be the same. So down here, which would have more volume? All of these are at STP. So remember, 1 mole is 22.4 liters. So if we say a mole of this and a mole of this, well, that'd be 22.4 liters. That'd be 22.4 liters. So those are equal. 2 moles would be 44.8 liters. That's 22.4 liters. That takes up more space. 22.4 liters, 2 moles would be 44.8 liters. That takes up more space. 500 molecules. Doesn't matter what gases they are, they take up the same amount of space. Okay? It'd probably be that's way less than a mole, so it'd be way less than 22.4 liters, but it'd be the same amount of space, however many milliliters of space that is. That's a mole, so that'd be 22.4 liters. That'd be one of these boxes, or a mole of helium. Those are equal. And that'd be half a mole. 44 grams is 1 mole, so that would be 22.4 liters. That's going to take up more space if we're at STP. So I could ask you a question like this. I could say, and this is not on here, but I could say, if you have 80 grams of O2, actually I'm going to change that. We'll say we have 96 grams of O2 at STP. I could say, how many liters of space does that take up? So a pretty easy way to do that would be go, well, you have 32 grams of O2 per mole of O2. Get into moles. And then if we're at STP, we can say that 1 mole of O2, 1 mole of any gas at STP, only gases, not liquids, not solids, only gases, take up 22.4 liters of space. So at STP, it's pretty easy. Okay, we can always do that. If we're not at STP, we cannot do that. Next section is on what I call final and initial state problems. I'm only going to do maybe 1 or 2 of these, but all these are just saying, okay, we have a gas at certain conditions. What if we change, like the pressure or temperature? What happens to the other things? So we really have this ratio. So initially we have the gas at these conditions. What if we change to these new conditions? What changed with it? So initial, final. Sorry about the little glare on the screen. So you have 30 degrees Celsius, remember that has to be in Kelvin, so we have to add 273 to that. So that's going to become 303 Kelvin. Does not matter what pressure's in, as long as it's the same on both sides. Does not matter what volume's in, as long as it's the same on both sides. So we have got temperature. And notice the temperature is not changing. It's staying at 303 degrees Kelvin. So we really can ignore temperature. It's going to stay the same on both sides. Or we can put 303 in on both sides. It's not giving us moles, so we can ignore moles. So we can just say P times V equals P times V, which is an inverse proportion. So 1.23 bars, that pressure, times 0.0247 meters cubed. So at this pressure, the gas takes up that much space. So we can say if the gas is compressed down to this, how much pressure did we have to put on it to get to that? So what is the new pressure if we go 0.00839 cubic meters? So we multiply these two numbers, divide by that, and your pressure is 3.62 bars. Okay, so you've got to increase the pressure from 1.23 bars to this to make it compress from there down to that, to make a gas get smaller. Let's do one more. You got gas has this volume at this temperature. What is the volume of the same amount of gas, so same moles, so we don't have to worry about moles, at the same pressure, so we don't have to worry about pressure, at a temperature of 10 degrees. So we don't have to worry about moles, we don't have to worry about pressure, so we can say our ratio is V over T equals V over T. We can do those two ratios. So 140 milliliters, temperature is 30. Remember, we have to turn it into Kelvin, so 273 plus that is 303. What is the volume if we lower the temperature to 10 degrees, which would be 283 Kelvin? So we're not lowering the temperature that much in terms of Kelvin temperature. Not going down that much. So our volume should just go down a little bit from 140 down a little bit. It's getting a little bit colder, shrink a little bit. So cross multiply, divide. Your volume there is 130.8 milliliters. All right, I'm going to leave the next questions up to you to answer. Have a great day.